So for problem E, for homework set number 2, if I'm not mistaken, you were given something where the voltage was 120 decibels, right? And I believe I give you a hint that 20 log of your voltage gain. Why is this being dumb? Hold on. 20 log of AV. Why does it keep erasing half of my strokes after the fact? That is weird. And that is going to be annoying. I literally just restarted this thing. All right, anyway. So we could divide both sides by 20. So that would give us 60 is equal to the log of AV. $120 divided by 20 is 60. It's 6. There we go. Sorry. All right. To get rid of the log on both sides, we would do 10 to the, so 10 to the 6th is equal to AV. And there we go. So 120 decibels is a million. So there you go. I think I'm about to sneeze. Oh, okay. So I had mentioned at the end of our last class meeting that we were going to look at some things with noise in it. So this is, let me get rid of this thing that's in the way. So I have a circuit right here that is just our simple comparator. And then I have a circuit over here that's utilizing positive feedback. And I want us to look at something, okay? So just to be clear, at present, I have the input signal as Vn plus N. So Vn plus N is defined up here. So what this is I have a simple sinusoidal voltage source. So it's going 0 DC offset, amplitude of 10. So it's cycling from -10 to +10 exactly one time. And then on top of that signal, I am superimposing some white noise. So there's a white noise generator function in LT Spice, and I'm just trying to add some noise on top of my signal. It doesn't have to be a huge amount of noise, but I just need some. So I'm going to run this simulation, and I'm going to look at my input signal. So we can see that it's a nice sinusoid. Let me change the color here. But it's got a little bit of noise superimposed on top. And now I'm going to look at the output signal of my comparator. Let me change the color of that as well, so that we can see it a little bit better. And so effectively, whenever I have noise around my reference voltage, which in this case is 3 volts, so my signal, my input signal effectively has a little bit of noise. And so when it moves around that 3 volts, it causes the output of my comparator to swing wildly up and down, which is exactly what the comparator is supposed to do. That being said, it's not particularly great from our perspective because we don't really see what's going on. We just have these weird spots where the output jumps high and then jumps low and then goes back and forth and all that kind of jazz. If we were to compare that to the output of this positive feedback circuit, we see that we have a nice smooth graph, but our values for where our signal goes high and low have changed. Let me change this to, maybe this dark green color will be easier to see. Yeah, that looks pretty okay. So the application of positive feedback, and I'm saying positive feedback because I have a resistor connected between my output terminal and my non-inverting input terminal. has caused things to smooth out, but it has also changed the relationship for when my output goes high and low a little bit. So right now, it's kind of hard to see what voltages are causing our signal to go high and low. So I'm going to look at this as a function of Vn. And I'm going to get rid of this Vn plus n signal. I'm going to get this thing out of the way. Don't want to delete anything. So we can see here that our signal, our output signal effectively changes states when our input is around 1. And then over here, somewhere between 6 and 7. So we're going to see if we can figure out the math behind why these particular resistor values causes our output to change states at somewhere around 1 and somewhere around 6.5-ish, instead of the 3 that we would expect because of our reference voltage. Okay. So let me remove all this junk. And let's now talk about our positive feedback circuit and throw some math at it to see what shakes up. And hopefully it doesn't continue to do this, but for whatever reason, it's been erasing some of my pen strokes after I have, I just updated and restarted my computer, so please bear with me. All right, so the first circuit that we're going to look at, and the one that I put in LP Spice, is what's called a non-inverting Schmitt trigger. It's getting annoying. SCHMITT trigger. Okay. And really does not like when I write G's apparently for some reason right now. Oh my God. This is annoying the shit out of me. Stay a G. All right, that slash is a damn G. I'm getting frustrated with this thing. Okay, so this weird slash thing right there is supposed to be a G. I do not know what's happening, but it's pissing me off. All right, goodness gracious. In my stylus, it just really doesn't like it when I draw the letter G.
All the settings on the top that you have up there, they're always on, like that squiggly line.
Don't know. Okay, I must have accidentally turned that on, didn't even realize it. Thank you. I have.
Try to draw that G.
Say a G, you bastard. All right, there we go. Thank you. All right, thank you for that. Yeah, I don't pay attention to any of the settings, so thanks. All right. So this is going to be our input terminal, Vn of t. So we have a time varying input signal. We're going to have some resistance here. I'm going to call it R1. Over here, we're going to have our op amp. I'm going to have my positive feedback path. This will be R2. Our output voltage as a function of time. And then on this pin, I'm going to put my reference voltage, okay? So this is the schematic diagram for a non-inverting Schmidt trigger. In order for us to understand how it behaves, we are going to employ our practical op-amp model. So this one is a little bit more difficult than any that we've drawn before, so I'm going to take my time to do this. As per usual, I am going to be starting with the practical op-amp model itself, and then I'm just going to connect all of the external things as I get to them, okay? So starting with my practical op-amp model, I have my internal input resistance, Rn. This is my non-inverting input terminal. This is my inverting input terminal. Over here, I have my dependent voltage source, AVOL times VD, where my voltage VD is always defined as the potential difference between the non-inverting input terminal and the inverting input terminal. Over here, I'm going to have my resistance R out, like so. And down here is my ground, right? So that's my practical op-amp model. Since I don't have a load resistance connected to this system, my output voltage is just going to be the voltage measured between the output terminal and ground. I have my reference voltage connected between my inverting input terminal and ground. So that's going to look like Vref down here. I have my input voltage source connected between my non-inverting input terminal and ground. Over here, let's just call it Vn for now. And now I need to consider, let's see, so I missed something there. I have a resistor R1 connected between my non-inverting input terminal and my input voltage. So I'm going to just sneak R1 in up here. Sorry for missing that. And then I have my feedback resistance, which is going to connect my inverting input terminal to my my non-inverting input terminal, can't talk today, to my output terminal. So here's where my feedback resistor should be. So we are going to make a couple of assumptions here in order to figure out how things work. And one of these assumptions is what we talked about in our last class meeting, okay? So I am going to assume that my resistance Rn is much, much greater than R1 and R2, the resistors that I'm using to bias my network. We'll see what impacts that has in a moment. I'm also going to assume, and this one actually won't really matter particularly, that my output resistance R out is much, much less than R1 and R2, which shouldn't have any impact on the behavior of this particular circuit. But if we had a load resistance here, we would need to make sure that R load was significantly greater than R out, or it would mess with that voltage divider circuit thing at the outside there. Okay. All right, so before we analyze this thing, does anybody have any questions about how I came up with this practical model representation of our circuit? Anything not make sense? Okay. So what I'm going to do is I am going to apply Kirchhoff's current law to the non-inverting input node. So I'm going to be adding this current, and this current together, and I'm going to see effectively what shakes out. So I should have my voltage V plus minus Vn divided by R1 plus V plus minus V out divided by R2 plus V plus minus V ref divided by Rn is equal to 0. That's what my KCL relation is going to look like, right? Now let's talk about what the implications of our assumptions mean here, okay? So if Rn is much, much greater than R1 and R2, then that means that this current term right here will be much, much smaller than whatever these current terms are, right? So I'm going to say that this is pretty damn close to 0. Well, if there's practically no current flowing through my input resistance, then that means that there's practically no voltage drop across my input resistance, such that V plus should realistically be pretty close to V reference. So now I'm just going to rearrange this thing. So what I will find is that V reference over R1 plus V reference over R2 is going to be equal to Vn over R1 plus V out over R2. And now I'm going to just play around with a little bit of algebra, right? So this is going to look like V reference times 1 over R1 plus 1 over R2 is equal to Vn over R1 plus V out over R2. 1 over R1 plus 1 over R2 is just the reciprocal of the equivalent resistance of those guys, right? So if I have R1 in parallel with R2, that would look like 1 over R1 plus 1 over R2. This is that exact thing, except without the 1 over bit. So we know that two resistors in parallel can be expressed as R1 times R2 over R1 plus R2. So I'm just going to multiply both sides through by the reciprocal of that to clear this thing. And what I'm going to wind up getting is that our reference voltage, V ref, is equal to R2 divided by R1 plus R2 times Vn plus R1 divided by R1 plus R2 times V out. And this is my characteristic equation for my Schmidt trigger. Now this seems like a kind of an odd relationship, but it is relating our input voltage, which we have control over, our reference voltage, which we have control over, to our output voltage. So we're going to play around with a couple of things. But we need to fundamentally understand what's going on here. Okay? So I want to go back to my graph. Why does this look Oh, because I accidentally scaled out or something. Let's rerun the simulation. There we go. And I'm going to get rid of with V out one curve because I no longer care about the comparator. So I want to describe to you guys effectively what's going on here. Okay. So our output voltage is low, right? It's at VCC minus or negative 10 volts. And it stays low until we hit this point over here, at which point it transitions to high or VCC plus. And then it stays high. As we bring our input voltage back down, it's actually going to stay high until we get to this point right here, at which it transitions back to low. So effectively, we have what's called latching going on. So our output doesn't change states until we go beyond some threshold, and then it changes states to up, and then it stays up until we go beyond some other threshold, at which point it goes back down. So this equation that we've derived is actually going to help us figure out what those transition things are, those transition voltages are. They have special names. They're called the upper and lower trigger limit, and they're what causes our output to switch from low to high and high to low respectively. Okay. So our lower trigger limit voltage V subscript LTL is the input voltage that causes the out to change from VCC plus to VCC minus. So if we wanted to calculate our lower trigger limit voltage, we would have our reference voltage. So if we look back at our LT spice diagram, our reference voltage is 3 volts. So we would have 3 volts is equal to R2 divided by R1 plus R2. So let's look here. R2 is our feedback resistor, so that's 10 kiloohms, divided by R1 plus R2, so that's going to be 10 over 13. Times our input voltage. That's what we're solving for. So this is going to be VLTL. Plus R1, which was 3 kiloohms, divided by R1 plus R2, 13 kiloohms, times VCC plus. Because we're figuring out what voltage causes us to transition from VCC plus down to VCC minus. For us, VCC plus was positive 10 volts. So take a moment here with your calculators and figure out what our lower trigger limit voltage should be. Three volts is equal to, so our reference voltage is equal to everything to the right-hand side of the equal sign. Let me make that equal sign a bit more clear. .9 volts. Okay. If we look back on our graph, I would argue that's probably pretty damn close to 0.9 volts. So this is where we transition from high to low. So this voltage is our lower trigger limit. Okay. Yes, Isaiah. So let me preface that my answer to this by saying that this isn't a comparator anymore. This is a Schmidt trigger circuit, and it's a Schmidt trigger circuit because we have positive feedback. So for a comparator circuit, the transition from low to high is at a single voltage, our reference voltage. There is a little bit of a, well, I say a little bit of a slope. So it is not truly a vertical line. There is a slope, but the slope is just incredibly steep. The slope of our line is related to our supply voltages and our open loop voltage gain. Because our open loop voltage gain is usually incredibly large, that's why the line looks damn near vertical. Okay? Now, one of the consequences of positive feedback is that our linear range is going to be even smaller, which means our slope of transition from low to high is going to be even more close to perfectly vertical. Okay. We're not going to really go into why that is because it doesn't really make a whole lot of sense in context of this class. But once we get really into the nitty gritty of designing amplifiers and looking at feedback in our electronics courses, we'll circle back around it. But one of the consequences of positive feedback is that our linear range is actually smaller. We already had a pretty damn small linear range in our open loop configuration to begin with. Did that help anything, or did I just confuse you? No, that's how the math we are assuming that there isn't a little bit of range, is effectively what's going on here, right? So we made some significant assumptions here. R1 and R2 were significantly smaller than Rn, so that we can say that there is no current flowing through that thing. No current flowing through that makes our reference voltage equal to V plus. We've made some assumptions here that are allowing us to get to a single number, but the single number agrees with our simulation. Yes. So, fantastic question. The input to my Schmidt trigger is the noisy signal. Do you see broad? No. So this is a better response when we have a noisy input. All right, so we have determined that our lower trigger limit voltage mathematically is 0.9. Looking at this graph, that looks like a pretty good estimate. Let's see if I can really pinpoint things here. So my cursor, my horizontal cursor is at 969.231 millivolts. So 0.96 volts. So it's not spot on because of the assumptions that we've made, but it's pretty close. So now let's calculate our upper trigger limit voltage. So the upper trigger limit voltage, the UTL, is the input voltage that causes V out to change from VCC minus to VCC plus. We're going to use the exact same equation as before, but we're going to put in the UTL and the correct value for VCC minus and see that we're going to get a different voltage, which will be our upper trigger limit, right? So we'll have 3 volts is equal to 10 kiloohms over 13 kiloohms times the UTL plus 3 kiloohms over 13 kiloohms, and VCC minus was negative 10. So take a moment and figure out what the UTL should be. Got something? 6.9 volts. All right. So let's see how closely that agrees with our simulation. 6.7. Pretty close. So this is a pretty good estimate considering the large assumptions that we've made about the behavior of this device as to how we can set our upper and lower trigger limits for our Schmidt trigger. Yes, Katie. You all constitute that? No. So there aren't a whole lot of circuits that we actually intentionally use positive feedback in. We have Schmidt triggers, and then we have astable multi-vibrator circuits, which is what we're going to cover next. And that is just an oscillator circuit. It's an interesting circuit because it actually doesn't have an input voltage whatsoever. We just let it run, and thermal noise causes it to switch between VCC plus and VCC minus at regular intervals. So it's how we make clocks. We'll talk about that in a minute. And yeah, but anyway. So we've got a pretty good estimate of how to calculate what our lower trigger limit is and what our upper trigger limit is. And it's just based on the resistors that we choose. And it's also based on our reference voltage. So this might not be intuitively obvious, but I'm mentioning this specifically because I'm going to ask you to design one of these in one of your design projects for the class. The reference voltage needs to be between your upper and lower trigger limit. If it were outside of that range, you would never be able to cause it to change the output to change state, right? So just as a heads up for your design project, if I give you what your trigger limit voltages are, you need to make sure that your reference voltage is somewhere in between, and then you'll just go through the math and figure out what resistor values you need to make things work correctly. Okay. One of your design project assignments is literally going to be a Schmidt trigger based analog to digital converter where you want the output to go high when the input voltage is greater than 3 volts and the output to go low when the input voltage is less than 2 volts. So instead of having a gray area in between where you don't know what things are, we use latching to force it into one state or the other, which would be a better analog to digital converter than your Arduino. All right. So we've talked about non-inverting Schmidt triggers. We've gone through the math to figure out how to calculate the upper and lower trigger limits to find what those are. Now let's take a quick look at an inverting Schmidt trigger. Okay. So for an inverting Schmidt trigger, we are literally going to have the exact same circuit, except that we are going to swap V in and V reference. Literally the exact same thing, except we swap V in and V reference. Okay. So our circuit should look something like this. Here's V reference, R1, I have positive feedback. Here's Vn. So I am not going to bother redrawing this circuit or reanalyzing this circuit. And the reason is because I really don't feel like I need to. Let me know when you guys are finished writing this down so I can go back to our previous results. So if this is the characteristic equation for our inverting, our non-inverting switch trigger, how do you think this is going to change for an inverting switch trigger? Swap V in and V out. That's literally it, because that's what we physically did to the circuit. So why would we need to reanalyze anything? If we apply Vn where V reference was, and we apply V reference where Vn was, we're going to get the exact same result with just Vn and V reference swap. So our governing equation will be Vn is equal to R2 over R1 plus R2 times Vref plus R1 over R1 plus R2 times V out. For our upper trigger limit, V out is going to be VCC minus. For our lower trigger limit, V out is going to be VCC plus, just like we saw on the previous example. So this one is actually easier to find our upper and lower trigger limit because Vn is what we're solving for finding the LTL and VET, right? So we literally just plug the numbers in and let them tell us what we want. We don't have to do any algebra whatsoever. For the inverting Schmidt trigger, the response is going to be flipped around. So effectively, we're going to start off high and it's going to stay high until we hit the upper trigger limit, at which point it's going to go low. And then it's going to stay low until we hit the lower trigger limit, which is going to cause it to go high. So it's just the exact opposite response, which is what we would expect because we switched the input and the reference voltage. Right? So those are Schmidt triggers. So now let's talk about the op-amp multi-vibrator circuit. So as I said earlier, this is a pretty interesting circuit. It actually employs both positive and negative feedback, but when it has both, the positive feedback is going to be the largely dominant term. So here we have our op-amp. Here's VCC plus. Here's VCC minus. My feedback resistor is going to be this resistor R1. Then I'm going to have this resistor R2, like so. So this is our output voltage. I'm not remotely close to finishing drawing up this circuit, but I want us to think about what this thing is right here. What is this circuit? It's a voltage divider, okay? If R1 and R2 are significantly less than the input resistance, then the voltage here at this node is just going to be R2 over R1 plus R2 times whatever V out is, right? This is actually going to serve as our reference voltage in the circuit. So we're using the output to establish our reference. So let's call this guy Vref. Then over here, we're going to have a resistance across the top. So like I said, technically this is negative feedback because we have a conducting path between our output node and our inverting input node. So this is our positive feedback path. This is our negative feedback path. And then we are also going to have a capacitor. So because I forgot to put a name on this, this is an astable vibrator circuit. Anybody know what astable means? Not stable. Okay, fair enough. So we actually have two stability points for this thing. So our output is going to swing between VCC plus and VCC minus, exactly like we saw in our Schmidt trigger. So those are our two stable states, and everything in between is just astable. So we're going to push it towards one or the other at any given point in time. Okay? So to figure out how this thing works, I am going to make a quick assumption here. I'm going to start by assuming that the voltage drop across my capacitor, so I'm going to label that as VC. So we are going to that VC is equal to 0 and that V out will be equal to VCC plus as our initial condition. Okay? We're going to talk our way through this qualitatively. But I'm not going to worry too much about the numbers. We'll just pack those on. So if V out is equal to VCC plus, then and VC is 0, then that means that there is some current flowing through this resistor R, so it's flowing up and around like so, right? So what we're going to see is that when our output voltage is high, our capacitor voltage is going to slowly charge. So it's going to increase from 0 until it reaches something. Okay. So I'm going to make a plot here. So this is going to be the out as a function of time. This one is going to be the ref as a function of time. And this one is going to be VC as a function of time. So we're starting out with our output voltage at VCC plus for some amount of time. And subsequently, our reference voltage is also going to be some positive value, right? I didn't mention that a moment ago, but it should be pretty obvious to figure out. We already talked about how this is going from a voltage divider circuit. So V reference is going to be a scaled version of V out. So if V out is positive, V reference will be positive voltage as well. It's just smaller because of our voltage divider circuit. And then our capacitor current is starting from 0. And it's going to gradually increase until it hits the reference. So what does it mean that our capacitor voltage and our reference voltage are equal? Our differential voltage is now 0, which means our output voltage can't be VCC plus anymore. So this is going to be the condition that causes our system to change states. So effectively, the instant our capacitor voltage overcomes our reference voltage, that's going to force our output voltage to swing negative. Because now our differential voltage is very slightly negative, and we have a huge open loop gain that we're dealing with. Right? So at this point in time, V out's going to swing negative, and it'll stay negative for a while. V reference is going to stay negative, or swing negative, and it'll stay negative for a while. And our capacitor is going to slowly discharge until eventually it gets to negative VREF, and then the cycle just starts over. Over and over and over again. Let me draw this better. Time that the output voltage stays on and the time that the output voltage stays high and the time that the output voltage stays low are equal. So we wind up getting a periodic square wave that's dependent on what we use as our supply voltage. So this is literally clock pulse. Mathematically, the period of our pulse is twice R times C, where R is that negative feedback resistor, C is the value of our capacitance, times the natural log of 1 plus beta divided by 1 minus beta, where beta is simply R2 over R1 plus R2, which is just our voltage divider ratio established by resisting R1 and R2. So we can use this circuit to effectively be a clock for something else where we don't necessarily have to have a quartz crystal oscillator or something like that to establish it. We're establishing it purely based on component values without a mechanical resonator in our system at all. All right, so let me see if I was smart enough to save my astable multi-vibrator circuit from a previous quarter, and if not, we might just, actually, I don't want to open it up in that file. We talked about our Schmidt triggers. Let me see what this is, but probably not what I want. Note that is very much a BJT differential pair. That has nothing to do with circuits too, so I don't know why I saved it in that table. Let me look in a different folder. Nope. Nope. All right, looks like I need to draw one really quickly. Get my keyboard out. Just going to slap something here. So as per usual, I'm going to use the universal op amp 2 for my op amp. I'm going to drop it over here. I'm going to set my supply voltages up really quickly. Let's use plus and minus 5 volts just for the sake of argument. VCC plus goes here. VCC minus will go down here. Me. Before probably. Yeah, that'll work. All right, dropping some resistors in. Let's make this one 1K, this one 2K, this one 10K. Let's make this capacitor, I don't know, a millifarad or something like that. I'm going to label some voltages here. So this guy will be VC, VREF, Vout. We'll go over here. And because I just made up values, we're going to have to figure out what the period of this thing is. We'll just let the simulation go and figure stuff out. Let's look at this for maybe 5 seconds. So if I look at my output voltage, so right now, and I'll change the color in a moment, but it's just staying 0 effectively. And the reason why it's staying 0 is because I'm using ideal components. So what I need to do is just give myself a little bit of stored energy. So I'm going to set an initial condition. It's going to make my capacitor voltage, let's say 10 millivolts to begin with, just so that there's some stored energy in the system. So dot IC, the voltage at node VC is equal to 0.01. If I rerun the simulation, things are starting to move, but I don't know what my timing is set to. So let's make this, instead of doing it 5 seconds, let's do 500. This might be an over exaggeration. Nope, that'll work. And we can see that our output now swings back and forth, exactly like what we should expect. Make this blue. If we look at our capacitor voltage, it's doing exactly what we would expect. Right? Started out at something a little greater than 0 volts. Because it was a little greater than 0 volts, going down first or whatever. And then our reference voltage here, doing exactly what we would expect as well. So we can see as soon as our capacitor voltage meets our reference voltage, our output swings 5, and then the cycle goes in the opposite direction. So exactly what we described just by looking at things qualitatively. All right, I've bored you guys enough for today. Have a great rest of your day, and I'll see you on Friday for negative feedback. If you have any questions about homeworks, etc., I'll be here for the next 15, 20 minutes.
Only on the assumption that
So for a real system, we don't have to make that because there's thermal energy in our system. So what I mean by that is like our capacitor is going to be close to 0, but it's never going to be exactly 0 because charge is moving. So it's going to be enough to actually kickstart this thing in a real system. That was just an assumption we made so that we can explain why it's going to wind up swinging back and forth. Realistically, once we wire everything up, it might take its time to get enough energy to kick one way or the other. Once it hits higher low, it's going to get
And it's power by the.
Yeah, so we have our supply voltages that are there. We're just establishing a periodic reference. So, because we have positive feedback, our output voltage is always going to be the case. So the out isn't going to be referenced. Our reference voltage is going to be R2 over R1 plus R2 times PL, but the negative of that same balance. So it's going to be a square wave. So that our capacitor voltage is always chasing our reference voltage. As we allow the capacitor to charge and discharge. It'll be up. If it's not up later today, it'll be up tomorrow for sure. The supervisor that I usually have do all that kind of calculating, instead of going back and forth to Arkansas every single day for some reason. So I'm having to do it by myself. So yeah, no, it'll be up shortly. Sorry.
I was gonna ask you about parking on the hallway.
Okay.
You put the video of exactly what's about. We didn't know what's on the last piece, where it said, make a relationship with any higher.
Right, so effectively what we should have observed, let me look at. Right. So. Was when VN was 4.5 volts. Oh, yeah. Yeah. For this one right here, VN was one capital.
Yes.
Okay. So when VN was halvable, VD1 was 3.5 volts. VD2 was -0.5 volts, and because of this, V out was 0. So effectively, we can see here that whenever VN is less than V low, the output is going to be 0. So this guy right here, VN is 2.5 volts. So that's between V high and V low, and our output is high. Right. So VD1 is positive, VD2 is positive, and because both VD1 and VD2 are positive, the output goes high. And then here in this last case, we have VN is 4.5 volts, which is greater than V high, and we see that the output is 0. So effectively, a window comparator works where if you're within the window, the output is high, and you're outside of the window, the output is low. So what I'm expecting is V out is equal to VCC minus for VN greater than V high. V out is equal to VCC plus for V low less than VN less than V high. And V out is equal to VCC minus or VN less than VN.
All right.
Is that it?
Yeah. All right. I'm gonna see that later.
I mean, I gave you 3 specific examples for a reason, so that you see them. So if your input voltage is between V low and V high, okay, the output is VC2 volts. If it's outside of V low and V high, the output is VC2 low. Okay. What? What is that working about? Include the effects of saturation distortion in your answer. What does saturation distortion mean? There we go. Same issue. All right. Sometime either this afternoon or tomorrow.
Okay. And hopefully, I'm kind of bottlenecked right now, after listening to your last lecture.
Yeah, I'll try to, so I have a speed worker that usually doesn't flow, but for whatever reason, she's just going back and forth to Arkansas every damn day right now, so I'm having to do it myself. Because I'm speaking 13 hours of classes, I just have to find free time to do it, and every time that we're doing it. So the best case we can hope for is this afternoon.
Am I still on your cell phone number? You can call me over the summer.
I would prefer that you email me first before you harass me on my cell phone, but it is what it is.
Okay, I'll just email you. All right, have a good day, Dr. Garvin.
Yep. See you later, Michael. Okay. So this city, yeah. One overall plus one overall is the reciprocal of. One over R one. Plus one over R two, which is two resistors, right? So I know that this can be rewritten as R one times R two over R one plus R two. Which means this thing is the same as R one plus R two over R one times R two. And I just use that to get rid of stuff. Okay. If you want to actually go through and do the algebra, it takes about 2 minutes. I was like that because you know what I'm trying to like. We have one over this thing. So there's this is X. So I have one over X, the reciprocal of one over X. The fractions inside the fractions can be annoying. I didn't want to deal with it, so I used the relationship that you're arguably familiar with. Okay. Yep. How do you identify the do I have a known voltage drop over two resistors? There's no ABJP, it is extrapolate.
Yeah, but it's operation, it's basically, I have to do that. I don't know exactly.
It is a very specialized transistor. I don't want to say specifically, you can definitely make comments and MOSFETs and all of that kind of stuff. But there are several different pieces that comprise phenomenon. So you usually have a transistor-based differential amplifier pair. So ground, and then usually, so this is a differential pair where you apply positive input here and a negative. So this would be your non-inverting input terminal, this would be your inverting input terminal. For an op-amp specifically,
I'm sorry, which direction is that right? Not right.
That's perfectly matched, so they're both, so these would both be NPNs or PNPs. Although for PNPs, we really split the whole so this is just a differential pair that's being biased by a BJT passcode current source. Realistically, you wouldn't actually use resistors here because they take up too much damn space. You would load this thing with a BJT current mirror. So that current mirror would look something like this. So this is what's known as a signal stage. It can only really drive capacitive loads. Its output resistance isn't high enough to be able to connect a resistive load and not have the gain. So, we would tie, this would be our offset node. And then we would usually tie this to secondary gain stage. Where that gain stage will probably be a N-based common emitter amplifier. That's just going to give us a very large inverted gain. And we would do a PNP stage so that we have headroom. If we did an NPN stage, like right here, we're going to talk about all this electronics next week, by the way. But effectively, this is going to have some stable DC operating point. If this was 5 volts, this would probably be somewhere in the ballpark of like 3.8 volts or whatever. If we used an NPN stage, that's just going to bring the output level, the DC level of that output even higher, so that we don't have a lot of headroom. So we'll use a PNP stage to bring the output lower, closer to the midpoint between whatever our power supply voltage is and ground down here. And then we would use an output amplifier stage that could be a push-pull amplifier. It could be as simple as just an inverter. If we use an inverter, it's not going, if we put a sinusoid in, we're not going to get a sinusoid out. It's going to introduce distortion, but it does just the opposite. So an op amp like a 741 or something like that will probably like 3 to 5 cents. So there's definitely your differential stage. Then there's a gain stage, then there's an output stage, and then you also have the stage that's for correction, offset, current biases, all that kind of stuff. We'll cover most of that crap in later.
Yeah, please, I don't get it by looking at it. Like, look at it a bit longer.
Which one? Upper and lower limits line.
Sure. Like the words? So the upper trigger limit is the voltage that causes the output to swing from low to high. The lower trigger limit is the input voltage that causes the output to swing from high to low.
I got the rest of the line and it's square and no line of
Let me get rid of some of this crap. I probably should have saved that, but I won't. So this is a non-inverting trigger. And so what's going on is our input voltage is on the x-axis, right? Our input voltage is ranging from -10 to +10 and then going back. So we start off with a negative input voltage. And our output is low, our output is low, our output is low, our output is low until we hit this point. This is our upper trigger limit. So when our input voltage exceeds our upper trigger limit, our output changes from VCC minus up to VCC plus. This part of the curve is our input voltage continuing to increase until we hit 10 volts. Then we're going to allow our input voltage to decrease. So it's going to be high, high, high. It's going to stay high as we get less than our upper trigger limit. And it's going to continue to be high until our input voltage gets to our lower trigger limit, at which point it swings low and then it stays low. So our output latches low until we exceed UTL, and it latches high until we get smaller than LTL.
This is what you said what's that?
This little blurb right here, oh, that's just an artifact from the simulation. It's just where it started or whatever. So realistically, it should just look like a nice rectangle. That's just a hiccup.
From the very back, it's really hard to see it.
Yeah.
And having glasses down, so I could it's 0 to 10 years.
Yeah.
And this is time-based, not.
No, so not time-based. So this is as a function of the input voltage. If we look at it as a function of time, it's negative until some point where it's positive, but we really need to put the input voltage on the graph as well. So we can see that our output is low until we're somewhere above 6, and then it swings high, and it stays high until we're somewhere around 1, and then it goes low and stays low.
Then it has to do it. When it keeps going.
It would repeat this over and over and over again, but I only have this set up to look at one cycle. I prefer to look at it as V in versus V out as opposed to V in and V out versus time, because it's easier to understand what's going on when you look at it as V out versus V in. And you get that arguably nice hysteresis graph. Yep. In my office, I haven't even really thought about it.
It's on good.
Yeah.
It's not due for like a week, so.
Okay. Oh, so shit, I've got to then. All right.
What is the idea of that? Why is it called that?
Because it's the reference voltage. That's what we're comparing things to.
So every time you want to use an offset, you want that voltage.
I don't want to say every time, but for the open loop configuration, yes, we can't just leave it dangling. So even if we ground it, we're effectively comparing things to zero. Or
There's always comparing V out.
V in, because we're trying to figure out, so VV, effectively the sign of the differential voltage is going to tell us whether the output goes high or goes low.
Is that
V in, so V plus minus V minus. Go to your notes for this class. When we first started talking about the practical op-amp class, so this would have been second grade class, one of the last things. Well, I can figure right there. VB is always the potential difference between the voltage at our non-inverting input terminal minus the voltage at our inverting input terminal. So whenever VB is positive, our output voltage will be VCC. Whenever VB is negative, our output voltage will be VCC minus, because our open loop voltage gain is so huge. It's the right, then causes saturation. It's really, really fun. So that's literally what's going on right here, right? So when our input voltage for our non-inverting comparator is really, really close to our reference voltage, it's still VCC minus until we effectively hit that reference voltage, at which point it swings up to the VCC plus. And then for our non-inverting, our inverting comparator, it's the exact opposite. So our differential voltage here is now going to be 3 minus VN. So our VB is still positive, so the output is positive until it gets to be negative, and then the output goes negative. The Schmidt trigger is just using our resistive feedback network to kind of make us not be constrained to just specifically that reference voltage. So if we look at our Schmidt trigger thing here, let me plot it as a function of time. Or not as a function of time, as a function of Vn. Let me get rid of that green plot because that's just a line with a slope of 1, right? So our reference voltage is 3 volts, which is right here. Now, instead of it triggering at exactly 3 volts, we trigger at a point greater than 3 volts, and we trigger at a point less than 3 volts. And that point is established by that resistor node.
That line is graphing V out.
Yeah, so the red line here is V out for my Schmidt trigger, and the x-axis is my input voltage as I allow it to range from negative 10 volts up to positive 10 volts and then back down to negative 10 volts. So our output is low until we get to our upper trigger limit, then the output goes high, and it stays high until we get down to our lower trigger limit, and then stays low, and then it repeats over and over and over again. All right, I've got to go get on an Entergy conference call.